All right, and good morning, everybody. So welcome back. I hope you guys had a great rest of your day yesterday, and the rest of your classes were as stupendously entertaining as mine. We all know that's not very hard, but it's something. And good morning. So today we're going to be going into section 9.3. All right, test about a population mean. All right, we've been doing population proportion. Now we're switching gears to population means. And significance tests with that. All right, so the first, we're going to go use a Desmos activity again, and I kind of like the Desmos ones a little better than Pear Deck as far as there's more math things I can do with them, which is why I've done them more often lately. The first, like, basically chunk of slides is kind of like notes, lecture, so to say, an example, and things like that. And then we will get into some practice exercises for you guys. And then we'll end with a little bit more kind of like wrap up notes and little odds and ends and such. All right, so that's kind of the idea for today. So I'm going to share the link for the activity in the chat. All right, everybody. I know most of you guys have done the check-in at this point, so thank you for that. And at the very least, you let me know how you're kind of feeling with that little graph. And most of you said you're tired. That makes sense. It's Friday. It's been a week. Trying to get back into the groove of school after spring break and all that fun stuff. So hopefully today goes well. Time goes fast and the end of the day comes real quick, and then you get to relax and have a good weekend and recharge those batteries. All right, so we're gonna get started with the lesson, and so I'm gonna do as I kind of do normally, and we'll keep adding screens here and move through. So first we have our little introduction. All right, section 9.3, test about a population mean. All right, confidence intervals and significance tests for a population proportion P are based on Z values from the standard normal distribution. Right, this is the previous lesson. Right, we use kind of the Z statistic, table A, it's a standard normal distribution. Inference about a population mean mu uses a T distribution. That means we're using table B with n-1 degrees of freedom, except in the rare case when the population standard deviation, sigma, is known, which typically we're not going to get. All right, we learned how to construct confidence intervals for population mean in section 8.3. Now we'll examine the details of testing a claim about an unknown parameter mu. All right, so we're kind of moving to the next step. Just as in chapter 8, we introduce conditions that should be met before we construct confidence intervals for a population mean, random 10% and sampling without replacement, normal large sample. These same 3 conditions must be verified before performing a significance test about a population mean. Right? So whether you're doing a confidence interval or a significance test, same 3 conditions apply. Right? We have to check that the data came from a well-designed random sample or randomized experiment. When we're sampling without replacement, we must make sure the 10% condition has been met. And we have to check that the sample is normal or large enough. Right? Just like with our confidence interval, if it's not normal and it's not large enough of a sample, then we have to graph the data and check to make sure that it is not strongly skewed and that there are no outliers. Right? In order to graph it, we do need to have all the data sample, right? If we're not provided that, then we just kind of do the best we can based on the information we have. Right? Hopefully, we get situations where we know the population has a normal distribution or the sample size is large enough. Otherwise, we have just a little extra work to do, but that's okay. All right, so again, same 3 conditions. Once we have checked conditions, we then move on to doing the math, conducting our test, so to say. And in this case, when we're dealing with population means, we're going to use the one sample t-test. Proportions, use the one sample z-test. Now we're doing one sample t-test. All right, when the conditions are met, we can test a claim about a population mean mu using a one sample t-test. Right. In this case, we choose an SRS of size n from a large population that contains an unknown mean mu. To test the hypothesis h sub 0 such that mu equals mu sub 0, compute the one sample t statistic. T equals x bar minus mu sub 0 divided by s sub x, which is the sample standard deviation, divided by the square root of n, right, the square root of the sample size. We then use the t-statistic to find the p-value by calculating the probability of getting a t-statistic this large or larger on in the direction specified by the alternative hypothesis in a t-distribution with degrees of freedom n-1. Right, and so we use the t-statistic very similar to the way that we use the z-statistic for proportions. We use table B, right, and then we find what proportion of those values are greater than or less than or just not equal to that null hypothesis. Right, it is important to remember, well, we'll get into that actually on the next slide. Right, does anyone need a moment on this slide to write anything down before I move forward? Please raise your hand. So since we're going to be using table B, here's some things to remember about table B. Table B gives a range of possible p-values for a significance. That means when we use table B, we will get an answer for the p-value that says it's between two values. We will typically not get an exact p-value when using table B, unless we somehow by chance land exactly on a specific value on the table, which we usually aren't. We can still draw a conclusion from the test in much the same way as if we had a single probability by comparing the range of possible p-values to our desired significance level. Right. Table B includes probabilities only for t-distributions with degrees of freedom from 1 to 30 and then skips to degrees of freedom 40, 50, 60, 80, 100, and 1000. The bottom row gives probabilities for degrees of freedom equaling infinity, which corresponds to the standard normal curve. And essentially, it's like if we have a sample size that is so incredibly large, it's essentially just going to be normally distributed, and we can basically just go back to using table B and such, or table A. If the degrees of freedom you need isn't provided in table B, use the next lower degree of freedom that is available. Again, the Price is Right rule. You cannot use a greater degree of freedom than what you get for n-1. Right, so even if I have a sample size of 80, right, 80 minus 1 is 79, I use the degree of freedom of 60 from table B, because that is the largest degree of freedom that is not greater than 79. Right, table B shows probabilities only for positive values of t. To find a p-value for a negative value of t, we use the symmetry of the t-distributions, meaning if I end up with a t-statistic that is like negative 1.8, I just find positive 1.8 on table B and the p-value that goes along with that. Because of symmetry, it's the same proportion as the negative value. Okay. Is there anything I can clarify about table B? We're going to move on then. All right, so next we have an example. This is an example that I'm going to show you guys the work for. I'm not expecting you guys to do it. This is our longer lasting batteries example. This will go through the 4-step process that we should be using when conducting a significance test. And it will show using table B and all that fun stuff, right? So for this, we're going to switch to OneNote and go through this example, but I need to go through that one. All right, so here we go. Actually, I'm going to zoom this in a little bit. Ooh. That works. Cool. All right. So a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. An SRS of 15 new batteries lasted an average of 33.9 hours. With a standard deviation of 9.8 hours. Do these data give convincing evidence that the new batteries last longer on average? All right. So again, my first step, right, was to collect all my data. Right, kind of get my summary stuff together. Right, we have the null hypothesis that mu is 30, which is the hypothesis that there is no difference. Right, there's no change from the regular batteries to the new batteries. They both have the same average battery life. The claim is that the battery life is longer, and so we get that mu is greater than 30 for the alternative. Sample size is 15. The sample mean is 33.9. Sample standard deviation is 9.8. And since there was no significance level stated, we will use alpha equaling 0.05 for our significance level. All right, and again, this is rather common to use 0.05 when nothing is given to use. Because it's one of the three that are very common, 0.01, 0.05, 0.10. 0.05 is in the middle, split the difference, we're good. It's just kind of a common thing to use. All right, so now that I have my numbers, so to say, all put together, I've pulled what I need out of my context. We move on to stating what we want to do. All right, we want to test the hypotheses of the null hypothesis that mu is equal to 30 hours versus the alternative hypothesis that mu is greater than 30 hours at the alpha equaling 0.05 significance level, where mu represents the true mean battery life of the new AAA batteries. So again, I want to point out that the statement here has three things. I have my hypotheses, the significance level, right? And I defined mu. You need those parts. Right? This tells the reader everything you're going to be using from our context. You've given a meaning to the things that you're going to use. All right. So we've stated, now we plan. If conditions are met, we will conduct a one-sample t-test on mu. And again, the one-sample t-test is my inference method. We check the random condition. The sample is an SRS. We were told that. We're good. 10%. We can safely assume that 15 is less than 10% of all the batteries. So we're good there. The normal large sample. Well, unfortunately, a sample size of 15 is not greater than 30. We do not know if the distribution is normal. And we don't have the individual data points from each of the 15 batteries to graph it. We were provided a mean and a standard deviation, so we're going to use that fact to just assume that the sample distribution is approximately normal based on the information we have. Otherwise, we wouldn't be able to continue with the problem. And they've asked us to do something here. Okay, so this is kind of one of those situations. This is the best we can do. I can't graph it to confirm that it's normal or that it's not strongly skewed or that it doesn't have outliers. But based on the fact that I have a mean and standard deviation, I'm going to assume that we're approximately normal. So then next, we do the math. We have to calculate our t-statistic first. Right, and so then this is our formula here. We have t equals x bar minus mu sub 0 divided by s sub x, which is sample standard deviation, divided by the square root of n. We get 33.9 minus 30 divided by 9.8 divided by square root of 15. If you're putting this in your calculator, please be careful. Put your parentheses around the stuff that's in the numerator and around the operations and things in the denominator to make sure your calculator behaves properly. All right, we get a t-statistic of 1.54. Right, we then start getting ready to use table B. We get our degrees of freedom here, 14. And we go to table B, right here. We find 14 here. We follow this across and we cross between 1.345 and 1.761, which between those two values lies 1.54. That means that my p-value is somewhere between these two probabilities of 0.1 and 0.05. I know that it's definitely going to be greater than 0.05 and definitely going to be less than 0.1, but it's somewhere in between. We don't know for sure based on table B. So that's how we get that the p-value is between 0.05 and 0.1. Right up here. We can also write this kind of more mathy if we want to by using an inequality. We do that by putting the lower value to the left, and we say 0.05 is less than the p-value is less than 0.10. All right, so we can write that a little bit more mathematically and say the p-value is greater than 0.05, less than 0.1. Is there any questions about the math part of this, the doing step? Anything I can clarify?
Yeah, I got a question. How do you get a square root of 15?
So that is part of my formula. So to calculate my t-statistic, I have to do the square root of n, where n is my sample size. And we have here at the very top, my sample size was 15. Right, and so based on the formula that we use here, I get the square root of 15.
Okay.
Does that help?
Yes.
All right, cool. Excellent. Any other questions? Anything else I can clarify? So the other option we have here for getting our p-value is to use technology. Right, we can use our lovely TI-84 calculators, which will pop over here. And based on what we have here, we can use, I believe it's the t-test. So we will go to stat, click over to tests, and the second option here we have a t-test. We'll hit enter. And we're going to put in stats. That's what we have. We don't have a list of data points Otherwise, we would use data. We have statistics, and so our null hypothesis is 30. The sample mean was 33.9. Sample standard deviation was 9.8. Sample size was 15. And we are going for greater than the null hypothesis, so we'll highlight the greater than mu sub 0, and then we'll go to calculate. All right, and so we get the t-score, or the t-statistic here, which is basically the same as what we calculated, 1.54, 1.54. And then our p-value, p equals 0.0727707, blah, 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 is in fact a value between 0.05 and 0.1. Now, obviously, we're getting an exact p-value here, which can be very useful in answering questions about our significance level, right? And so this is the technology way of finding our p-value when we're given the statistics. There is also a strategy to use when you don't have the statistics. And you just have like a t-value. We'll look at that later. Is there any questions about how to use the calculator in this scenario?
How do you know when it's greater or less? Like which one are you going to choose?
So that's based on our hypotheses, right? Our alternative is that mu is greater than 30. 30 is our mu sub 0, our mu not hypothesis, our null hypothesis. And so in the calculator, when we set up our test, it's the wrong test. I'm going to select the greater than mu 0. If my alternative was that it was less than, then down here I would select the less than option. I can also select the not equal to for the two-sided test. And that's all dependent on the direction of the inequality for your alternative hypothesis.
Okay, thank you.
You're welcome. All right, so we've done our math here. Now we write our conclusion. Because the p-value is greater than alpha equaling 0.05, and we know that even if we didn't use the calculator, because the inequality we have here says that it is greater than 0.05. We fail to reject the null hypothesis. We do not have convincing evidence that the new batteries last longer than the regular batteries. And that's it. Notice again, I'm taking that second sentence in my statement and writing something about what this means in context. Right. Is there anything else I can clarify about this example? So the next screen here is nothing we're going to do today. This is just a video of me actually working through the example. If that's something you're interested in seeing, you'll have access to that if you want to go back into the Desmos activity. I might also post it somewhere else on the Canvas page. I haven't decided yet, but we're not going to watch that now because I just explained it. So then we get to the first example problem. All right. And this is about checking conditions. The composition of the Earth's atmosphere may have changed over time. To try to discover the nature of the atmosphere long ago, we can examine the gas in bubbles inside ancient amber. Amber is tree resin that has hardened and been trapped in rocks. The gas in the bubbles within amber should be a sample of the atmosphere at the time the amber was formed. Measurements on 9 specimens of amber from the late Cretaceous era give these percents of nitrogen. So we have our values here. Explain why we should not carry out a one sample t-test in this setting. Please explain down here in the text entry window. All right, awesome. So there are several reasons why our conditions fail in this case. Many of you guys have at least one of those reasons in your explanations. You know, let's see. Yeah, sample size is too small. Some of you guys said, right? It is less than 30. Doesn't work. Someone mentioned that when you graph these data points, you get something that is skewed to the left. Very good. So excellent. Those are a couple of very good reasons. We're going to switch over here and look at all the reasons just to cover our bases. All right, so number one, we don't know if this was random. We were not told how the sample was collected. We don't know if 9 is the population. Maybe that's all the samples they have. We don't know how they got the sample. We don't know if it was random, so that condition fails. Sample size of 9 is less than 30 and not sufficiently large. Here's a graph of the data. All right, a histogram here. Obviously, it is skewed to the left, so that's a problem. And yeah, so we have several reasons why this does not work out. Right. But very good work. Excellent. So now we're going to practice finding a p-value using table B. So you should get a range of p-values for this question. And I will put a link to the to table B in the chat here. If you guys give me just a moment, I'm going to read through the problem first. Hemoglobin is a protein in red blood cells that carries oxygen from the lungs to body tissues. People with fewer than 12 milligrams of hemoglobin per deciliter of blood are anemic. A public health official in Jordan suspects that Jordanian children are at risk of anemia. He measures a random sample of 50 children. We're going to assume all necessary conditions have been met. The sample mean hemoglobin level was 11.3 milligrams per deciliter, and the sample standard deviation was 1.6 milligrams per deciliter. Calculate the test statistic T, and then find the p-value using table B. So I want you to use table B for this example. I do want to point out that you do have extra ways of answering this question. If you have the means to kind of like write on your screen, you can actually scribble in this space up here. You can also choose to type in this space. You can choose to type math in this space up here, or you can use the text entry box below, or you can do your work on a piece of paper and upload that image using the upload image option in the text entry box. So you have many, many ways that you can choose to show your work and do your work in here. Please choose the one that you like the best. And then lastly, as you guys get started here, I'm going to put a copy of table B in the chat. Give me just a moment for that. All right. I know that some of you are still working on this, and that is totally okay. We're going to talk about it. So here we go. So for this question, right, we have the provided information that the null hypothesis was that, well, I will pull the information out. The null hypothesis was that mu equals 12. The alternative was that mu is less than 12 milligrams per deciliter. Our sample mean was 11.3. Our sample standard deviation was 1.6, and we have a sample size of 50. All right. Calculating our t statistic, we get 11.3 minus 12 divided by 1.6 divided by the square root of 50. And we end up with the t statistic of negative 3.094. And remember, on table B, we cannot find a negative value, so we will find 3.094 somewhere on the table, or as close as we can get to it. We're going to use degrees of freedom of 49, which then means on table B, I believe the closest we get will be 40. All right. So then we refer to table B, which all up. Right, so we have table B here. And we get 40 down here, and we will follow this over until we get something at around 3.094, which is going to happen between 2.971 and 3.307. Right, and because we're between these two values, we look back up to the top of the table, and that means that our p-value must be between 0.001 and 0.0025. Right, which is what we have here in our inequality. Right, 0.001 is less than the p-value, is less than 0.0025. We can then also, as we saw in our previous example, we can use the t-test to find this more exact value. And using technology, we end up with the p-value of 0.0016, which is in fact between 0.001 and 0.0025. Okay. And that was all we were asked to do in this problem. We just asked to find the p-value. Is there any questions? Is there anything I can clarify? So now we have a one-sided test example. Right, suppose you carry out a significance test of the null hypothesis being that mu is equal to 5 versus the alternative hypothesis that mu is less than 5 based on a sample size of n equaling 20 and obtain a t statistic equal to negative 1.81. And so in this case, we do not have a sample mean or sample standard deviation given, but we are just told right off the bat what the t statistic is. All right, find the p-value for this test using table B or technology. And then what conclusion would you draw at the 5% significance level and at the 1% significance level? All right, so you'll write two conclusion statements. Now, obviously, in this case, we do not have the context. So your conclusion can simply say we do not have evidence for the alternative, or we do have convincing evidence for the alternative. Right. So I'll give you all a few minutes here using table B. We're not quite at technology for this one. This uses a different thing in the calculator than what we've seen. So I suggest just using table B. And then we will reconvene and talk about this. So I know that may not have been enough time. That's okay. If you're not done, that's fine. We're going to talk about this. So if you're still working, please continue. We'll go into this example. So we have our one-sided test here. And again, I've listed out our pertinent information at the top here, the null hypothesis, the alternative, our sample size, and our t statistic, because that's all the information we have. Using table B, we get degrees of freedom of 19. Right, which leads us to a p-value that is between 0.025 and 0.05. Right, the p-value is greater than 0.025 and it is less than 0.05. We can also use technology, and we can use our TCDF function, which you find in the TI-84, not under stat, but under distribution. So if we go second and hit this button that says vars, right above it says distr, distribution. That gives us this menu of options. All right, we're going to use the TCDF option. That is a t statistic distribution, or t distribution, sorry. All right, we'll hit enter. On the lower bound, we just need a large number. the upper bound, we can in fact use the negative value when using the calculator. So we'll put in negative 1.81, and our degrees of freedom was 19. That's all the information it needs. It is using our t distribution, okay? It already knows that that's the table it's referring to. We'll hit enter, we'll hit enter again, and we get 0.043. 0.07, blah, blah, blah. And again, this value is in fact less than 0.05, but greater than 0.025, and is a more specific p-value that we can use. However, it does not change our conclusions. So again, we can use the tcdf function here if we like. Right. And at our 5% significance level, because the p-value is less than alpha equaling 0.05, we reject the null hypothesis. We have convincing evidence that mu is less than 5. Because the p-value is greater than alpha equaling 0.01, because we know that it's greater than 0.025 and 0.025 is greater than 0.01, we failed to reject the null hypothesis, so we do not have convincing evidence that mu is less than 5. Right, so depending on the significance level, we get a different conclusion for each condition. Is there anything I can clarify about this example? Anything I can explain further? So lastly, we're going to do this one last example here. Right, suppose you carry out a significance test of the null hypothesis that mu is equal 128 versus the alternative that mu is not equal 128 based on a sample size of n equaling 72, and obtain a t statistic equal to 1.10. Again, you want to find the p-value for this test using table B or technology, and then what conclusion would you draw at the 5% significance level and at the 1% significance level? So once again, we're doing table B and drawing a conclusion. In a few minutes, we will talk about it. All right, guys, we're going to talk about this one. And again, this one's a little tricky because this is a two-sided test. All right. So here is some work for this. So now again, when we have that two-sided situation, we basically get twice the p-value. All right. We use symmetry, right? And if you guys, if we look back at this screen here, screen 4, when we're on a two-sided situation where mu is just not equal to the null hypothesis, we get two tails in our distribution, right? The proportion greater than the t statistic we found and the proportion less than the negative t statistic that we found. Right, so that means when we use table B, we will find the p-value corresponding to t equaling 1.1 and then double it. We multiply each of those sides, essentially, because we get that inequality by 2. So if it was one-sided, we would have the p-value between 0.1 and 0.15. Because it's two-sided, we now double each of those, and we get a p-value that is between 0.2 and 0.3. All right, so the p-value is greater than 0.2, but it is less than 0.3. All right. We can again use the tcdf function, but in this case, we will set it up as a one-sided test, and then multiply the result by 2. Right. Since the p-value of 0.275 is greater than alpha equaling 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that the mean mu is different than 128. We have the same conclusion when the significance level is alpha equaling 0.01, because if it's greater than 0.05, it's definitely greater than 0.01. All right, is there any questions on this example? Anything I can clarify?
For the DF,
Mhm.
in the table B, we didn't have 71. So which number did you use?
60. 60 is the largest degree of freedom on table B that is not greater than 71. Let me pull up my picture here. All right, so 71 would be between 60 and 80. But again, we have to go to the lower degree of freedom. We can't go above 71, so we go back down to 60. Right, and so 60, right here, we'll see 1.045 and 1.296. 1.1 is between those two. We follow that up, and that's between 0.15 and 0.1. And then again, we double both of those endpoints to get what the p-value is between.
Okay, thanks.
You're welcome. Is there anything else I can clarify? So there is a few more slides here that is essentially just notes and kind of like tying a couple other things up as far as some other situations and where we would use a one sample t-test. We're not going to get into that today. We're already just a little bit over an hour here, which is the most I want to keep you guys. So we'll wrap this up on our next class. And make sure we review those last couple slides. But this is all the examples I had for you guys. So I will stop the restriction here. You're more than welcome to look at those next few slides on your own if you like. You'll have that available. We'll stop sharing my screen. But essentially, we've covered all the parts of Chapter 9 that we need to cover. We've gotten the basics. The Chapter 9 assessments are available. They've been posted into Canvas. If you would like to look at those and begin those, that is entirely up to you. And next week, I'm hoping to get into a little bit more of the preparations for taking our AP exam. And hopefully, I think next week we're able to get into that software. And if we are, we'll look at using it and practicing with it, and possibly doing some practice scenarios. If not, then we'll begin chapter 10, and I'll talk about that when we get there. So other than that, guys, it is Friday. Have a great rest of your day, and we will see you next week.